Welcome to Power Up, a podcast show that brings life to some of the stories on power electronics technologies and products featured on powerelectronicsnews.com and through other AspenCore media publications. In this show, you'll hear both engineers and executives discuss news, challenges, and opportunities for power electronics in markets such as automotive, industrial, and consumer.
Welcome to today's podcast. Today's episode is brought to you by our sponsor, Renesas Electronics. I'm your guest host, Alia Shokat, Editor-in-Chief of Power Electronics News and Associate Editor at EDN. During this chat, we discuss how the Renesas GaN offerings support the requirements of different power applications across sectors like AI infrastructure, solar energy, onboard chargers, and DC-to-DC conversion in EVs. Today's discussion includes Primit Parekh from the Power Product Group at Renesas Electronics. He is the Vice President and General Manager of the GaN Business Division. We are also joined by Pietro Scalia, Senior Director of Power System Marketing and Architecture at Renesas. The power conversion within each of these sectors is shifting towards more power-dense, efficient, modular, and intelligent power architectures, with trends towards high-voltage buses, bidirectional energy flow, and fewer conversion stages. Today's focus will be on infrastructure and renewable energy, with a discussion of how the rapidly growing GaN semiconductor sector can be a key enabling technology to drive these system-level improvements. GaN is experiencing significant growth in power electronics across low and high voltage applications, including 650 volts and above. GaN offers manufacturability in standard silicon fabs and thus scalability. The wide bandgap semiconductor also benefits from a high power density and high efficiency, enabled by high switching frequencies and key material properties. Finally, GaN offers massive system integration through embedded features such as bidirectionality, a feature that is novel to GaN. Primit and Pietro join me today to discuss how Renesas Electronics is addressing these design developments, sharing insights into Renesas GaN Power's current initiatives, including 800 volts AI infrastructure, as well as single-stage bidirectional GaN power conversion for solar microinverters and automotive onboard chargers, a growing market segment. So Primit, let's start with you. Can you please introduce yourself and tell us a little bit about your role in Renesas?
So this is Primit Parekh, currently Vice President of the GaN Business Division at Renesas. I've been immersed in semis and notably wide bandgap technologies and GaN business and scaling businesses for the last 25 years now. In the early days, first 10 years or so with GaN LEDs and RF transistors, and then the last decade and a half with power electronics as an entrepreneur, introducing and scaling GaN into key markets, which is where we co-founded Transform back in 2007 to focus on GaN power and its growth through multiple strategic, financial, customer opportunities, partnerships with our superb team. And then we did its public company transition in 2020. We were listed as TGAN on NASDAQ. And then I also drove a strategic process as its CEO, culminating into a successful acquisition by Renesas in June 2024, which is how we are part of Renesas now, which is excellent. And then in our business division at Renesas, we have both discrete GaN and IC-based products that combine GaN with controllers, drivers, and we call this the GaN ecosystem. And then not only that, but taking a step further, working with Pietro's team, other Renesas' divisions, by combining GaN with Renesas controllers and a broader company portfolio, we aim to introduce winning combinations, reference designs, not just the device, but the device, the circuit, the solution that address everything from fast chargers to megawatt class AI servers in the coming years.
Thank you very much, Primit, for the introduction. Let's move to Pietro. Can you introduce yourself and describe your role at Renesas?
Sure, Alia. So my name is Pietro Scalia, and I'm the head of Power System Architecture and Marketing at Renesas Electronics. I joined about 2 years ago, and I come from a, let's say, quite long journey of about 30 years in power across TI, onsemi, Ericsson, Siemens, to name just the most relevant companies. And today supporting power growth is more and more a system story, right? To demonstrate our components, fits, and solve application challenges for our customers. Therefore, being on top of the hottest architecture that drive power across the market segments, building hardware to demonstrate the performance of Renesas solutions is a key role of my team. GaN is today spreading across different markets and applications, and as a consequence is becoming a common element used in these solutions, from industrial automation to robotics, so in this case specifically about motor drive at high and low voltage, to data center infrastructure, to racing applications in automotive like OBC and DC-DC. My team is spread in the 3 regions, defining and supporting combo power solutions for all of these market applications.
Thank you, Pietro. Okay, so Primit, given your extensive background in GaN, I wanted to ask you, what does it take to make a compelling GaN product today, and what are the challenges that come with this?
So Alia, fundamentally, the power market needs simultaneously delivering on many performance metrics, efficiency, power density being primary ones, and then robustness and reliability, ease of use, and manufacturing scale. And all of this have to be at attractive price points. Power application, as we dig down a layer, need what is a normally off transistor for just simple safe operation. And this is achieved by either a D mode, depletion mode, or an E mode, enhancement mode offering. Now it turns out that nature has made GaN to be D mode. It is just what it is when you make GaN. That's not us or any particular company. And then to make it E mode, you require additional wafer process steps. Of course, it can be done, of removing charge with ensuing damage and damage control. And then this P-type gated layers to achieve a positive threshold voltage to make it enhancement mode, so off when no bias. So this works well actually at lower voltages, and it does work well at higher voltages also. But at higher voltages, it comes with a number of challenges, say 650 volt and above, where noise immunity, transient tolerance is key, and including issues like saturation current drop at higher temperatures, higher dynamic, which is operating resistance. What you see is not what you get. That results in higher losses and lower robustness, especially at higher power when we go into kilowatt class GaN. So for us, what we have done for high voltage GaN, Renesas is a D mode in the cascaded configuration, combining best of both worlds, GaN and silicon. High speed, high voltage, high channel conductivity GaN, switching it with a robust threshold gate compatible with standard gate drivers. That comes from the silicon part. The heavy lifting of the voltage and power loss is done by GaN. And then this combination goes in extensive package varieties, which is not simply available with other GaN technologies. So we pair our D mode GaN HEMT, the GaN transistor, with an optimized low voltage, normally off silicon MOSFET. GaN is high voltage, silicon is low voltage, through a stacked die approach, which is excellent example of heterogeneous integration. No additional package area, no additional wires, zero inductance connection. So very similar to effectively for the customer, like a single chip solution, and with low inductance, with no or very little or no ringing, and increased immunity, DITT, DBTT immunity. This configuration architecture is a very good fit in both hard and soft switching application, and numerous examples and customer adoption studies we have shown. Then equally importantly, combining with all of this technical approach is the IDM approach, and talk more about that a bit later. But the ownership of GaN wafer manufacturing is very key in control of IP, manufacturing, and ultimately the price points that will be in range of silicon to ultimately one day displace silicon completely.
Thank you very much, Primit. That was a very thorough response. I appreciate you touching upon GaN's scalability, cost, transistor topologies, etc. Thank you. We'll shift over to Pietro now. This is a question for you, Pietro. From your power systems and market perspective, can you describe some of the most exciting applications of GaN technology and how Renesas GaN addresses these main challenges?
Yes, it's really exciting. GaN is expected to grow in high double-digit CAGR to support unprecedented power challenges driven by the most important industry megatrends. It started with high-value IoT consumer electronics, specifically chargers, right? But it's now spreading to applications like renewable energy, storage systems, servo motors, AI data center infrastructure from grid to core, automotive charging system, e-mobility with 2, 3, or 4-wheelers, where high power levels are required with greater efficiency in smaller system size, achieving very high power density from hundreds to eventually thousands of watts per inch cubic, reducing system cost. In general, wide bandgap components, in particular gallium nitride, is enabling this revolution. A true renaissance in power electronics is really being fueled by the advent of these fast and smallest power switches that ever been made. Let me give you a few examples of applications that drive, let's say, hyper-demand growth. In data center, the new 800 DC architecture shift is pulling in high power GaN very fast, with 800 to 48 or 800 to 12 direct DC-DC conversion in computer rack, demanding power conversion at frequencies very close to megahertz, where SiC falls short, as well being a play now for novel bidirectional GaN in topologies like Vienna rectifier for the AC-DC sidecar power rack, which enables architecture towards the grid. Due to its excellent switching characteristics, D-mode GaN excels both in hard switching and in soft switching, like in these examples that I just listed, as proven by these two different examples in the same application ecosystem. Another key beneficiary of GaN are solar microinverters, cycloconverters, and onboard electrical vehicle chargers matrix topologies, where the unique bidirectional device, BDS, ability enabled by GaN lateral architecture, which is not possible directly to implement in silicon or silicon carbide devices, simplifies AC to DC or DC to AC conversion with single-stage topologies, and this cuts part count and improves system efficiency and cost. GaN has also some application in high-performance AI PCs and gaming power, let's say hundreds of watts up to kilowatt. And Renesas is really offering to its customers products that fit in all of these areas.
Thank you. Thank you for covering key applications for Renesas and GaN. So PRIMIT. We're shifting to PRIMIT again. So it looks like Renesas is ready to support the large adoption of GaN in a range of applications. Can you describe how Renesas GaN can address key challenges such as controlling switching times and protecting devices from events like overvoltage and short circuits in critical systems?
Yes, so now we move into the heart of our execution and how we do it. So all Renesas GaN products, firstly, are built on our fundamental GaN quality and reliability platform. For example, products feature high immunity for ESD, 1 kilovolt HBM human body model is standard, sometimes even 2 kilovolts, and qualified at least to JEDEC standards and well beyond. So this is a must. In addition, what we do, to conventional JEDEC standard testing for high temperature reverse bias, gate bias, accelerated testing, temp cycle, power cycle, all of these things. We carry additional call test, reliability tests targeted specifically to GaN, including things like dynamic on resistance, switching and transient reliability, and low temperature reliability, not just high temp, but low temp. Renesas GaN we have designed for high margin with the 650 volt rating, continuous rating, and on top of that, 800 volt transient rating with leakages well under control. And this is an enabler for key industrial as well as automotive applications. So, sometimes folks say that silicon carbide is rated for 750 volts, GaN is not. But well, in that case, it can be said GaN is rated for 800 volts, in fact, in terms of transient ratings, which is what really matters during switching. Last but not the least, we've also presented accurate accelerated lifetime models, which are built to ensure use case operating life. This is another topic in itself, but what we have shown, in contrast to some others in GaN, that how to do this accurately for GaN, stressing GaN, accelerating GaN failure modes in the right schemes that are seen actually in the operating life, and invoking the right failure modes. So we have set a benchmark for this and also published it. All of these thoroughly designed tests ensure product robustness in all environmental conditions, not only consumer and industrial, but also for automotive use. The net result today is 400 plus billion hours in the field in our customers' applications, including both low power and high power multi-kilowatt applications with a sub 0.1 fit rate, a claim no other GaN manufacturer can make today, especially the high power applications part. So then while the D mode, depletion mode GaN can switch fast, like we said, we enable designers to benefit from the low crossover and switching losses. GaN is meant to be switch faster, which is a key why it is high efficiency and lower losses. But if slower transients are needed to meet EMI targets or other application-specific needs, say DVTT limits in motor drives, for example, we allow for slew rate control. A close examination of our topology reveals an inherent coupling, capacitive coupling, between the gate of the silicon low voltage transistor and the drain of the GaN high voltage transistor, which offers a feedback loop controlled with a simple gate resistors and allowing tuning of both turn off and turn on transitions, just like any other power device. Our GaN is technologically ready to enable the capability to withstand short circuit events, a key requirement in many motor drive applications. This is done with our patented approach where the gate of the D-mode GaN is tuned to limit the saturation current to increase the short circuit withstand time with a very simple single layer modification in die design. So depending on needs of our customer and the application, whether 1 microsecond, 2 microsecond, or even 5 microsecond, the design can be tailored to meet specific needs with a predictable trade-off with on resistance, again, just like any other semiconductor power switch. So all of this can be done in GaN also. With the D-mode architecture and enabling standard drive electronics, we offer discrete GaN products that can be just used like silicon or silicon superjunction with excellent protection and control at the circuit level, or we can also offer, and we do offer, integrated products like SIPs, system in package, and power stages, which integrate our controller driver with matched GaN chips. Integration where it makes sense and offers a customer benefit is what we do.
Thank you, Primit. Thank you. So Pietro, let's shift to the recent single-stage bidirectional GaN solar microinverter reference design. Your system and architecture team has been realizing this design. What performance benefits are you observing when implementing GaN in microinverters?
Yeah, for this, Aliyah, let's go a bit more technical in the details of what my system architecture team has been implementing. The solar microinverter reference design uses bidirectional GaN in a DAB, dual active bridge single stage topology, versus traditional flyback plus inverter dual stage topology. It generates efficiency increase and cost decrease together. GaN bidirectional device enable current flow and voltage blocking in both directions with one smaller device with half the current rating or double the RDS on, as you want to see it, replacing two traditional larger power switches back to back. In theory, delivering a 4-to-1 semiconductor area benefit along with a 2-to-1 power switch component count benefit. So starting from the solar panel 100-volt low voltage network, the single-stage microinverter enabled by GaN consists by a DC-AC full bridge utilizing Renesas low voltage 80-100 silicon REXFETs, in future can be low voltage GaN eventually, followed by transformer isolation and a direct AC to AC conversion on the secondary side with a 650-volt GaN BDS device. This platform minimizes component count versus the traditional multi-stage DC-DC flyback converter and then DC-AC conversion stage, and enables higher efficiency from panel to grid of about 97% CEC, so California Energy Commission efficiency. Both off-grid and on-grid operating modes are enabled by the reference design. And beside the power discretes, we have described multiple other Renesas components, such as the RA62 MCU, some LDOs, buck converters, drivers are utilized in the total solution. In this single-stage architecture, the controller, in fact, also plays a crucial role. In order to achieve today's stringent EMI and THD distortion standards, tight current control is required. At the same time, cycle-by-cycle current monitoring enables safe and reliable operation. Leading microinverter companies like Enphase, for example, have announced novel cycloconverters-based microinverters that can utilize Renesas 650 GaN BDS devices with very high efficiency and good cost structure.
Thank you very much, Pietro. Okay, so the last question here is going to be for both of you. The supply chain for a new technology is always key to enabling its large-scale adoption in the market. On top of system advantages, we have the system advantages we've reviewed so far. So how is Renesas going to support the transition to a significant volume increase that the market seems to require?
Yes, this is an excellent and a fundamental point. We believe in technologies, especially like GaN, where manufacturing scale with wafer-level ownership is key, i.e. the IDM model will win. So our GaN devices are made with proprietary epitaxial layers grown on low-cost silicon substrates. With EPI IP, we have developed over more than 15 years back from the original Transform days, and even actually prior to that, some of our IP, resulting in very stable dynamic on resistance with a high breakdown voltage. This is paired with high quality wafer fab and device processes. We run GaN on a silicon line, but the steps are proprietary. In Renesas' own GaN fab, maintaining end-to-end control of process flow and IP, know-how, and traceability. We do today, our products in the market are on 6-inch. Wafers are from US, Taiwan, and Japan, so geographically diverse. And now we are moving to 8-inch with a US manufacturing footprint already announced with a partner where we have entered into certain licensing arrangement of our IP. So that is going to be very key now, going to 8-inch and then having a worldwide footprint, including US manufacturing. GaN scale itself is progressing very rapidly. Adoption is increasing. This trend is expected to continue with scaling to 8-inch GaN. There has been a lot of talk and publicity also for 12-inch GaN, and it will happen, but where it makes sense. For example, on low voltage GaN below 200 volts, where there are thinner GaN layers required, that may go to 12-inch GaN first in due course of time. Coupling the wafer fab with industry standard and performance, high performance packaging options, which we again uniquely enable the whole suite of packaging with our D-mode normally of architecture, such as the standard TO, the good old TO220, TO247 are still desired by customers for ease of thermal management, to new surface mount low profile packages, both bottom side cooled and top side cooled, with or without Kelvin source. And with respect to a pinout, that D-mode GaN is still compatible and pin-to-pin with other configurations, other offerings from the industry, which is a need for customers. And it remains a natural fit for high voltage applications, both unique capability as well as multi-sourcing. Another key point is ecosystem of solutions as we scale. So Renesas GaN, we are focused on enabling a superior user experience through our ecosystem. By that we mean both GaN and ICs working together in tandem in solution and including integration where it makes sense. We have a rich roadmap of GaN, controllers and drivers optimized for key GaN topologies, integrated products like SIP system in packages and power stages that you'll be hearing a lot more in future. And then one step above, combining this with Renesas' broader company portfolio of microcontrollers and other power ICs with reference design and our winning combination, we deliver turnkey GaN-based solutions that address everything, again, from fast chargers to megawatt class AI servers in the coming years.
Yeah, and let me add some even more aggressive perspective here, Alia. Ultimately, for completely taking over silicon devices, or at least dominating new power system designs, GaN cost needs to match or even be better than silicon. And this is possible thanks to the density, to the higher density that GaN actually enables. So while already in promising distance today for several products and certainly offering better value cost at system level due to the savings that you implement beyond the device with thermals, magnetics, component count, GaN scale is progressing rapidly with increased adoption. This trend is expected to continue with scaling to 8 inches GaN, and where it makes sense, for example, at low voltage GaN below 200 to 12 inches GaN wafers, which will happen in due course of time.
Thank you. Thank you very much, Primit and Pietro, for the informative chat. I really appreciate your time. Definitely keep in touch, and we're excited to see what's in store next for Renesas and its GaN business. Thank you.
That's great. Thank you very much for your time and coordinating.
Thank you very much.
That brings us to the end of this episode. Stay tuned for more news and technical aspects about power electronics. If you are listening to this on the podcast page at eetimes.com or powerelectronicsnews.com, links to articles on topics we have discussed are shown on this page. Power Up is brought to you by AspenCore Media, and the producer is James Eade.